think that we should begin with today's session, the third session of the Pump Up online training seminars. I will be watching if someone more wants to join. Today's session is going to be led by Amparo León from the Polytechnical University of Valencia. And to not waste much of your time, I think I can give the floor to Amparo. Welcome.
Thank you, Irini. Hello, everyone, and welcome. Can you hear me? Yes?
Yes,
Thank you. Well, as Irini said, my name is Amparo León Minet, and I'm a researcher at Universitat Política de Valencia. And it is a pleasure to be here today as part of this Train the Trainer seminar. As you know, this session is organized within the framework of the Erasmus Plus Pump Up project, an European initiative focused on improving skills and training in heat pump technologies for the heating, ventilation, and air conditioning sector. The project brings together different partners across Europe to develop practical and accessible learning resources, including training modules, an online course, and virtual assistant app. The aim of these seminars is to share the main results of the project and support trainers, professionals, and educational centers in using these materials and spreading this knowledge. By the end of today's session, you will understand three essential things. First, how to dimension and select the physical components that distribute heat through the building, which are the meters, the pipes, and the materials. Second, how to choose and configure the control systems that make the whole thing run efficiently and safely. And third, how to assess cost, both upfront and ongoing, and how to navigate the landscape of European subsidies and incentives that can make or break project's economic viability. Thank you very much for joining us today, and we hope you find this session useful and interesting. I'm going to share my screen so we can see the course. As you've seen in previous seminars, this is the Pump Up course, and we are going to start with the most basic. The single most important concept that you must understand before we discuss any component is this. Heat pumps operate at fundamentally lower temperatures than the boilers they replace. A traditional gas boiler pushes water through your radiators at 70 to 80 degrees Celsius. But a heat pump, by contrast, operates most efficiently at a flow temperatures between 35 to 55 degrees Celsius. This is not a limitation. This is, in fact, one of the reasons heat pumps are more efficient. But it has implications for every component in the distribution system. Let me give you an example. You take a standard double panel radiator of 700 millimeters high and 1000 millimeters wide. And this radiator delivers 1061 watts at a flow temperature of 70 degrees Celsius. Now you connect it to a heat pump that is running at 50 degrees Celsius, and the same radiator delivers only around 1010 watts. And this is not a subtle difference. This is halving the performance. And this single fact drives most of the design decisions we will discuss today. So how do we solve this temperature challenge? Well, there are essentially two strategies. Either make the radiators bigger or switch to a different type of heat emitter that is inherently better suited for our low temperature operation. Let's start with radiators, which are the most common heat emitter in existing European buildings. Radiators are affordable, widely available, and easy to install, which is why they remain the default choice in both new construction and retrofits. But with a heat pump standard, radiators needs to be oversized by a factor of 3 to 7 compared to what you will install with a boiler. And in some cases, you might need to add extra panels, increase the height, or incorporate convector fins to boost the output. Modern aluminum radiators have become the preferred solution for heat pump installations. As you know, aluminum has superior thermal conductivity compared to steel, which means you get more heat output per square centimeter of radiator surface. Also, fan-assisted radiators represent another approach when they use small integrated fans to force the air across the radiator surface. Now, we can talk about the underfloor heating, because it's in many ways the ideal partner for the heat pump. The principle is very simple. Instead of concentrating all your heat output in a few radiators mounted on your walls, you spread it across the entire floor area. The floor itself becomes the heat emitter. And because the surface area is so large, you can achieve comfortable room temperatures with low water temperatures, as low as 30 to 35 degrees Celsius. This is the sweet spot for heat pump efficiency. The trade-offs: underfloor heating is more expensive to install, more complex to retrofit into existing buildings, and it responds more slowly to temperature changes than radiators. Manifold placement and accessibility are also important design considerations. But for new buildings and major renovations, underfloor heating combined with a heat pump are arguably the gold standard for comfort and efficiency. Now that we have the emitters selected, we turn to the plumbing that connects them. In any hydronic heating system, hot water travels from the heat source through the feed pipes to the emitters, and then they return via the return pipes. These usually run in parallel, and the routing should be as efficient as possible to minimize both material use and heat loss. There is a common misconception that I want to address right away, that many people believe that all heat pump systems require 28 millimeter pipes, and this is not true. The correct pipe diameter depends on three things: the total heat load, the temperature differential between flow and return, and the maximum allowable flow velocity, which typically is of 1 meter per second. If you exceed that velocity, you get noise and vibration in the system. And if you undersize the pipes, you restrict the flow and reduce efficiency. If you oversize them, you waste money and may get a poor heat transfer. As a general guide, main feed pipes are typically between 28 and 35 millimeters in diameter. Branch pipes are usually 22 millimeters, and final connections are 15 millimeters. In cases of microbore systems, which usually use 8 to 12 millimeters, these cases exist but require careful management of temperature differentials and flow rates. And for materials, the choice essentially comes down to copper versus plastics. Copper is the industry standard for a good reason. It is extraordinarily durable, of lasting between 50 to 70 years. It has excellent heat transfer properties. It resists corrosion, and it even has natural antibacterial properties. And the downsides are mainly cost and the need for skilled installation. We also have PEX, which is cross-linked polyethylene, that has become increasingly popular, especially in retrofits. It is flexible and easy to work with, and is way less expensive than copper. And it's particularly well suited for underfloor heating. However, it's typically less durable at high temperatures and has a somewhat shorter lifespan for around 40 to 50 years. Regardless of the material you use, you must account for thermal expansion. Pipes expand as they heat up, and if this expansion is not accommodated, using bellows, expansion loops, or flexible connections, you risk stress fractures and leaks. Having designed our distribution system, now we need to control it, and in this section we will talk about the control options. A heat pump without proper controls is like a car without a steering wheel. It might have all the power you need, but you have no way to direct the efficiency. Good control strategy is what separates a merely functional installation from a one that delivers genuine comfort and economy. The first layer is the time controls, the control time-based. There is an ongoing debate among specialists about whether heat pumps should be run intermittently or continuously, and let me walk you through the three different approaches. First of all, the intermittent option means that the system switches off at the end of the predicted occupancy period and switches back on before the next one. It is the most energy efficient approach in theory, but you need to build some margin, both in the heat source and in the emitters, to ensure that the building can reach comfortable temperatures within a reasonable time after a cold start, especially during the coldest days of the year. Continuous operation means that the system is always enabled. It does not mean that the compressor is running non-stop. It means that the system is always ready to respond to a thermostat call. This approach provides the most stable indoor temperature, but it's potentially wasteful and may not comply with building regulations that require some form of time clock control. So we have the combined approach, which is called setback operation, and is usually the best compromise. The system is running continuously, but at different temperature set points through the day. Imagine overnight, when everyone is in bed, the target temperature drops by a few degrees. During the workday, when the house is empty, it drops again. But before the occupants return, it ramps back up. This can be particularly sophisticated when different emitter types are used. For example, underfloor heating, which is slow to respond, might start ramping up hours before radiators in the same building. We also have temperature controls. Temperature controls should be available in every single room. For radiators, this is typically the radiator valves, which are inexpensive passive devices that regulate flow based on room temperature. And for underfloor heating, individual room thermostats connected to some control valves are the standard. Fan coil units have their own built-in controllers or are connected to separate room thermostats. But the key principle here is simplicity. Whatever controls you install must be easy for the end user to understand and operate. A technically perfect system that the homeowner cannot figure out is a system that will be misused, and it will lead to complaints and inefficiency. We also have weather compensation, which is more accurately described as ambient air temperature load correction, and is one of the most impactful control features for heat pump efficiency. The principle is straightforward. On a mild autumn day, your heat emitters do not need to operate at maximum output. Weather compensation recognizes this and reduces the flow temperature from the heat pump accordingly. Lower flow temperatures means the heat pump operates more efficiently. It is doing less work to produce its unit of heat. Over a full heating session, this can significantly reduce electricity consumption. And we also have optimized controls, which takes this concept further by learning how the building responds to heating. The systems monitor how quickly the building reaches its set point temperature after switching on, and they adjust start times based both on indoor and outdoor conditions. Imagine a Monday morning that was very cold and the system took 2 hours to warm up. But on Thursday is forecast to be milder, and the system might delay its start by 30 minutes. Many modern heat pump manufacturers now build these self-learning algorithms directly into their controllers. Lastly, hot water production deserves a separate attention because it operates at different temperatures from space heating. While in space heating, we use flow temperatures of 35 to 45 degrees Celsius, especially with weather compensation, hot water generation typically requires at least 55 degrees Celsius. And this is not a comfort requirement. This is a safety requirement. Legionella bacteria, which causes a serious form of pneumonia, thrive in water between 20 to 50 degrees Celsius. And they stop multiplying at temperatures above 50 degrees and are killed by temperatures above 60 degrees Celsius. For this reason, the water stored should be periodically heated to at least 60 degrees Celsius in order to pasteurize the water. And this should be used on a weekly basis, but it can be required more or less frequently. And before we get into the numbers, I want to give you the broader picture of the European heat pump market because it directly affects cost, availability, and the financial support your clients can access. In 2022, the energy crisis hit Europe very hard. Gas prices soared, and suddenly the gap between electricity and gas cost narrowed dramatically. Heat pumps, which had always been more efficient, became economically compelling almost overnight. The result: sales surged by approximately 40% across the top European markets, from about 1 million units sold in 2021 to 2.5 million units in 2022. Then came the correction. By 2023 and 2024, the prices stabilized, governments introduced price caps, some subsidy programs ended or became uncertain, and new building construction slowed down by about 20%. Heat pump sales then declined by about also 20%. And this is the classic boom and burst pattern of a market driven by external shocks rather than steady structural change. But here's the good news. The fundamentals have not changed, and by 2026, 2027, the market is expected to recover to its pre-crisis growth trajectory. Energy future prices are projected to fall 30 to 40% between 2024 and 2027. Subsidy programs are being relaunched. Countries like Austria and Germany are introducing bans on fossil fuel heating in new buildings, and the long-term trajectory is clear. 10 to 15% annual growth in heat pump sales across Europe after 2027. So starting with the cost, let us break down what things actually cost. For air-to-water heat pumps, the most common type for residential applications, installation in a standard 3-bedroom home in Central to Northern Europe ranges between 12 to 18,000 euros. But there's an enormous variation by country. Germany sits on the expensive end, when an 8 kilowatt air-to-water heat pump is about 28,000 euros. And this is because of their stricter technical requirements, higher efficiency and sound insulation standards, and more complex installation procedures. The UK, on the other hand, the same system costs around 14,000 euros. In Mediterranean countries like Spain, Italy, and Greece, those are significantly cheaper, with costs typically ranging between 3 to 10,000 euros, depending on the system size and the property requirements. Premium systems like 12 kilowatt output can reach 27 to 40,000 euros before subsidies. But after subsidies, which can cover up to 55% in some programs, the net cost can drop to around 21,000 euros. Now, this is for air-to-water heat pumps. For groundwater source heat pumps, these are more expensive, typically exceeding the 20 to 30,000 euros due to the drilling and groundwork. And in South Europe, ground source installation costs are between 10 and 20,000 euros. But once installed, the ongoing cost consists of three main components: the electricity consumption, which is by far the largest, and we will do a practical example later to calculate the cost. Then the maintenance typically ranges from 100 to 300 euros per year for residential systems, and this includes filter replacement, coil cleaning, refrigerant checks, and control system verification. For repairs, these are harder to predict, but can range from minor fixes under 100 euros to major component replacements exceeding the 1,000 euros. But the economic attractiveness of heat pumps is profoundly influenced by the electricity to gas price ratio. In Norway, where electricity is cheaper and the ratio is favorable, heat pumps have reached a 98% market share in new heating installations. In countries where electricity is expensive relative to gas, adoption is lower. High performance heat pumps can reduce energy consumption by 20 to 40% compared to standard models, making efficiency a key factor in the long term economic case. And as always, no discussion of heat pump economics will be complete without addressing subsidies. The European Social Climate Fund, becoming operational this year in 2026, represents the most significant financial commitment to date, up to 86.7 billion euros, primarily targeting vulnerable households and microenterprises. This fund will be financed partly through revenues from the new emission trading system for heating and transport fuels, which begins in 2027. You can see the web page of the European Social Climate Fund online. This is the link, if you want to check it. And at the national level, support varies considerably. Germany offers rebates up to 40%. The UK provides £7,500 in grants. France has MaPrimeRénov'. Italy has the Conto Termico scheme that can reverse up to 65% of installation costs, etc., etc., etc. But the summary, the important part is that these programs can reduce the net cost by 20 to 65%, depending on location and system type. And as always, as a system designer, you need to be aware of the incentives available in your market because they can transform the marginal business case into a compelling one. And they should be part of every conversation you are with a client. So the theory part has been explained. And in summary, today we have covered the three pillars of the system design and costing. First, the physical components, which are the emitters, the pipes, and the materials, and how to size and select them for low temperature operation. Second, the control strategies, from simple time clocks to weather compensation and self-learning algorithms that ensure the system runs efficiently and safely. And third, the economic part, from the initial cost to operating expenses to subsidies and incentives. If you do this course, you have the question and answer section, which I think the most interesting part of these question and answers are the material aspect, mainly how copper, PEX, and other materials commonly used in the heat pump pipework behave on the system, and how the choice of the pipe material impacts the lifespan of the heat pump system. Next, as you can see, there are the self-assessment questions, which I did at 80% when I did this test. The questions are easy to understand, but are not that easy. They make you think, they make you relearn, they make you check every small detail that you have seen in the previous lessons. And last but not least, there is a practical exercise. The first one is calculating the operation cost, only the operating cost of a heat pump. And the second one is calculating the cost, including also the maintenance of the heat pump. The first one, as I said before that we were going to do, is very easy. you can do it in two different ways. The first one, you have an estimate of how many kilowatt hours the property consumes. In this case, we're going to assume 12,000. We know our system's efficiency, which is measured by the seasonal coefficient of performance or the coefficient of performance. And we have to divide it to get the electricity consumption, because it's not the same the annual heat demand, which is heat, to the electricity consumed. We do this division, and in this case, we're going to assume the seasonal coefficient of performance of 3.5, and we have an electricity consumption of 3,429 kilowatts hour. Now we have to multiply it by the electricity cost. We have the electricity rate. We are going to average it to 15 cents per kilowatt hour. And we have that the price per year, it's 514 euros and 35 cents. To this cost, we should also add the maintenance costs, which are usually 200 euros, depending on the system. And we get an estimate, if we round it up, an estimate of 800 euros per year for our system working, consuming 12,000 kilowatts per hour annually. You can make better estimate if you know approximately the hours of operation per day, the days per month it is going to work, the months per year it is going also to work, because in some cases maybe you do not turn the heat up in April or May because they are milder on, or if you are an enterprise in August or July you are closed, so the system is completely off. And also knowing the power consumption of our heat pump. These are some easy calculations, but they being a rough estimate that you can use to your clients. And as I said before, you must also explain them all the incentives that have available, because maybe the price might take them back. But if you bring the incentives and subsidies, it can be reduced, as I said before, in the European case, between 25 to 65%. So thank you so much. I think this is it for today's session. If you have any questions or need any specific answers or something to be clarified, I'm here in case you have any questions. Irini, we cannot hear you.
Yeah, I just realized. I just said thank you very much for your presentation. It was really delightful and in detail. I myself understood more things about heat pumps because we're the management part of the project. So it was very, very delightful to have you with us today. Sorry for the noise. And if there are no questions for today, just to remind everyone that the fourth session is the day after tomorrow, Wednesday, the 13th of May. We continue with module number 4. That is developed and is going to be presented by Tartu, a vocational educational training center in Estonia, which is also a partner of the Pump Up project. So Wednesday, same hour, module 4 from the Estonian partner of the Pump Up consortium. And that's all from our side. We hope to see you again on Wednesday. Thank you very much.
Thank you very much.
Thank you. Bye.